Yeah, I'll go ahead and introduce Jackie. Good morning, everyone. We are delighted to introduce to you our speaker of today's seminar, Dr. Jacqueline Johnson. Dr. Johnson has been instrumental in teaching SAS software training at various academic campuses nationwide and fostering collaborations with faculty members to build the future analytics workforce. Dr. Johnson holds a PhD in biostatistics from UNC Chapel Hill. She brings to the table a valuable blend of academia and industry experience. Having worked as a biostatistics faculty member at the UNC Chapel Hill School of Medicine and a biostatistician at Novartis and Roche companies. Her proficiency in statistical analysis of a clinical trials data is a testament to her distinguished career, which began in 2009. In today's seminar, she will introduce us to longitudinal data analysis. So let us extend a warm welcome to Dr. Johnson.
Thank you so much, Lily. That was a great introduction. I want to add a few things just to give you some context to my experience with this topic. So as Lily was saying, my background is largely in biostatistics, and I've worked in industry, the pharmaceutical industry, for a lot of my experience, as well as in academic clinical trials. And so when you're conducting some sort of clinical trial study, so this is drug development, or you're assessing some treatment of some disease, something like that, we're collecting data on people. And in almost all cases, those studies, you're going to bring in the patient multiple times, right? So they'll come into your study for some baseline visit, and then there are a series of follow-up visits. And these are what are called longitudinal data. And we're going to get all into what longitudinal data are and everything, but clinical trials, we use longitudinal data in almost every study that we worked on. So I'm very happy to be here, and I'll go ahead and get right into this talk. So let's first start with a definition of what we mean by longitudinal data and longitudinal data analysis. So the key feature of longitudinal data is that they are repeated measurements taken on a subject through time. So for example, I've got my Apple Watch here, and my Apple Watch records my sleep every night. And so I've got my minutes of total sleep every night, and that's collected every day. And so I could do an analysis over time of my total amount of sleep. That data are collected over time is an important distinction here. We're not talking about the general class of repeated measures data. In particular, we're not talking about what are called clustered data. So an example of clustered data, these are data that you can think of as correlated, but not due to time. So an example of clustered data might be children within a classroom, right? And so, and maybe you're trying to assess their math scores on some standardized test. And so because of the ability of the teacher, or maybe the funding of the school or something like that, you might expect students within the same classroom to be correlated, right? But that correlation is not due to observations being taken over time, okay? So we are constricting ourselves specifically to data that are taken over time. And the reason that that matters is we're going to see that observations taken on the same subject are correlated, right? So I'm sure several of you guys have an Apple Watch. And so if we looked at my sleep measurements and then one of your sleep measurements over time, my measurements are more likely to be like each other than like yours, for example. And we're going to need to model that correlation, okay? And we're going to need to pick correlation structures that have to say something about time. All right, so this is just kind of something to give us some motivation about what we're going to talk about here. I'm getting a little bit of background noise. I'm going to mute some of the participant lines. All right, and welcome everybody. It's great to have you here. So what we're going to do here is we're going to be able to look at trajectories over time. So we're going to be able to distinguish changes over time within a subject. And then we're also going to be able to look at changes between subjects at specific time points. All right, and we can group subjects as well. And I'm also going to tell you about ways to fit models where you can estimate subject-specific regression parameters. So maybe you actually want to estimate the trajectory over time for an individual subject. All right. And one other comment I want to make about longitudinal data analysis is that the data that we're talking about here, this is data where you have a short series of time points taken over many subjects. So the number of time points is pretty small and the number of subjects is pretty big. So maybe you have, say, 2 to 20 time points and you have 200 subjects, something like that. So the number of time points is much smaller than the number of subjects. And the reason that I want to point that out is I am not talking about what's called a time series today. So a time series, an example is the stock market, the Dow Jones Industrial Average, something like that. And so we have an observation for that every day the stock market is open, right? But it's really just one subject taken over a great many number of time points. So we're not going to be talking about time series today. So let's talk a little bit about the distinction between longitudinal data and what's called cross-sectional data. Cross-sectional data are data that are taken at just one time point. So what we're looking at here is we've collected blood pressure, and that's on the vertical axis, and then age, that's on the horizontal axis. And we've collected both of these variables on a person at one time point. So each of these dots represents one person at one time point. And we can certainly say something about the relationship between blood pressure and age here, right? As age increases, blood pressure increases. But now let's look at some longitudinal data. So we can collect these same variables, but we can collect them multiple times on a subject. And so now, instead of having one time point per subject, we have these trajectories. So here's the trajectory for the first subject, here's the second subject, third subject, etc. We can still say something about the general relationship between blood pressure and age, right? We can still say something about the fact that as age increases, blood pressure increases. But now we'll also be able to say something about trajectories for each subject and also how blood pressure is changing over time as a function of age, right? We can also say something about the variability of blood pressure at different time points, right? So maybe how blood pressure changes over time is really pretty different for different people. So there's a lot of variability between subjects. So we can characterize that variability as well. What we're going to see today is, and I mentioned this in the beginning, is that we're going to need to define what is called a correlation matrix, or specifically a variance covariance matrix for our data. And this data is going to describe the correlation of observations within the same subject. But before we get to the case of longitudinal data, I want to talk about what this matrix would look like for cross-sectional data. So here I have 4 subjects, and I've measured some outcome Y on them. So it's 10, 7, 12, 11. And then I've measured some predictor X, 4, 2, 6, or 8. All right. And over here on the right, we have their variance covariance matrix. Now, in this case, every data point comes from a different subject, right? And we've taken data only on one time point per subject. So here, these diagonal entries, these represent the variance of that observation. And we make a very important assumption about those variances when we perform an analysis on these data. In particular, we assume they have homogeneous variance. And so and this is one of the assumptions that we make in a regular regression analysis. So this is the regression analysis you would learn about in your first statistics course or your first linear modeling course. So our variances are going to be homogeneous, but then these off-diagonal entries, these represent the covariance between any pair of observations. And since these observations come from different people, and we have one time point per person, all the observations are statistically independent. So their covariance is 0. So the variance covariance matrix in this case is diagonal. We just have variances on the diagonal, and everything else is 0. But now let's talk about what this type of matrix is going to look like for longitudinal data. So here, let's say we still have 4 subjects, and we still have observed this one predictor, and it doesn't change over time. So our X doesn't change over time, and it's whatever value this is. But now we've observed our outcome y at 3 time points. So for subject 1, their outcome was 10 at the first time point, 6 at the second, and 6 at the third. And for each one of these subjects, you could graph this subject-specific trajectory, right? So that's just their outcome over time. Now what we need to do in order to characterize the variance-covariance matrix for these data is we need to do a transformation. So this data set is what is called wide. So the repeated measures are in columns. But ultimately, to analyze these data, we need a data set that is long. And so what we're going to do is we're going to take our wide data set and turn it into a data set that is 1 observation per subject per time point. And so you'll notice for subject 1, the previous data set had 1 observation, and now it has 3, 1 for each time point. You'll see that the predictor X, it's not changing over time, so we just repeat its value. And then we have our outcome Y, and it is changing over time. And so now we have 3 rows for every subject. The variance-covariance matrix in this case is what is called block diagonal. And each of these blue blocks is going to be the variance-covariance matrix for a subject. All right. So this blue one is the variance-covariance matrix for subject 1. This is the matrix for subject 2, etc. Now, subjects are still going to be independent of each other. So if I see all these white blocks out here, these represent the covariance between different subjects. So these blocks are the covariances between observations of subject 1 and observations in subject 2. So subjects are still independent. But inside this blue block, these are observations from the same subject, and they are no longer going to be statistically independent. And so the whole goal, if I can pick out maybe a few main take-home messages here, the whole goal of longitudinal data analysis is to put some structure in this blue box. So we have to pick a way to model how observations from the same subject are correlated. And again, that correlation structure is going to be informed by our time points, since this is longitudinal data. I'm not going to show you too much math, but I want to give you an introduction here just to some notation for a model that we're going to consider. Because when we're talking about the variance-covariance matrices, we need to talk about different choices that make sense. So I need to give you just a little bit of notation here, but most of this will not be math notation. So in an introductory statistics course, in an introductory regression course, you learn about what is called the general linear model. And the model statement that we have here is for that general linear model. And so let's talk about this particular data case. Our outcome is in a vector that we denote as y. And again, this vector is stacked. So we have 1 observation per subject per time point. Then we have this vector beta. These are unknown population regression coefficients that we wish to estimate. So these are going to be the regression coefficients for all your predictors, all the variables that you want to relate to your outcome. Then X is going to be the design matrix for beta. That's where all your data for the predictors come in. So this is a fixed matrix. And then epsilon, this is a random matrix. So this is a vector of random errors. So this captures all the variability in your outcome Y that's not explained by X beta. All right. Now, in a general linear model, we make a very specific set of assumptions on epsilon. And this is it's both specific and restrictive set of assumptions on epsilon. And these aren't going to hold for our longitudinal data. So this is important. So we assume epsilon comes from a normal distribution with mean 0, and then it has that diagonal covariance matrix. So it's sigma squared, the variance, 1 homogeneous variance on the diagonal, and then all the off-diagonal entries are 0. Now, by the way, let me say something here. I am going to confine my discussion today to a continuous normally distributed outcome. Everything that we're talking about, you can extend these ideas to discrete outcomes or continuous outcomes that don't have a normal distribution. It requires slightly more sophisticated mathematical machinery, but everything that we're going to do today can also be performed for other distributions as well. But I'm just going to talk about normally distributed data. So this is our general linear model, something we're all very familiar with in our first regression class. But we want to model some longitudinal data. We have a clinical trial. We've collected various measurements on patients over time, and we need to model that data. So let's talk about the framework for our longitudinal data, and that is called the general linear mixed model. So we still have our outcome Y, and we still have our fixed effects X beta, so that has not changed. But now we have two new pieces. This first piece, gamma, this is a vector of what are called random effect parameters. It's through this vector that you're able to give each subject its own subject-specific trajectory. All right, so in my clinical trial, let's say I've got 100 patients in my clinical trial and I want to estimate the trajectory for each patient. I'm going to do that through this vector gamma. Now here's some important notation here, and this is notation for SAS. This is the notation that SAS uses in our documentation. If you're reading about mixed models in another textbook or in another software, they're probably going to use different notation, but this is the notation that we use at SAS. We need to ascribe some notation to the variance covariance matrix of our random effects. We're going to call that G. So that's our first thing, is we have a covariance matrix we need to estimate, and it's called G. Gamma, the random effects, also has its own design matrix, and that's called Z. And this is where we tell SAS, is it a random intercept? Is it a random slope? If our random effect is time itself, this is where the actual time values would come in. All right. So we have this random effect gamma, and its covariance matrix we call G. Now epsilon over here, we saw that in the previous model. We saw that in the general linear model, but we're going to relax the assumptions on epsilon. So in the general linear model, when you have fully independent data, you require observations to be independent and have homogeneous variance, but we're not going to do that for longitudinal data. So we're no longer requiring all observations to be independent, and we're definitely not requiring them to have homogeneous variance. So we're going to have a general covariance matrix for epsilon here, and we're going to call that R. So here's the second big thing I hope you take away from today, which is we need to model the covariance structures in two places here for longitudinal data. G, which is the variance covariance matrix for gamma, and then R, which is the variance covariance matrix for the residual error epsilon. All right. And by the way, please feel free to ask questions as you go along. Now I'm going to talk about how to fit these models in SAS today. If you're not familiar with the SAS programming language or with SAS software, SAS has a variety of statistical procedures that are grouped into various different kinds of tasks. I'm going to show you in a demonstration today how to use the mixed procedure. And here's some syntax for the mixed procedure in SAS. All SAS procedures are executed through a sequence of statements. And in the SAS programming language, a statement for a procedure starts with a keyword. And so in this case, the first statement is going to start with the word proc. Then we have the name of the procedure, which is mixed. And then there are several statements within proc mixed, each of which starts with a keyword. So we have, for example, a class statement, a model statement, random and repeated statements. And I'm going to show you a demonstration about how to utilize these statements in order to fit the model. And if you're not a SAS programmer, or if this is kind of your first or kind of a beginning exposure to SAS, you don't really need to worry too much about the syntax right now. But I'll say kind of a couple of main ideas here, is that we need to specify the fixed effects in our model. So those are the betas, the X betas. We're going to do that on the model statement. And then we need to specify G. That was the variance covariance matrix of gamma. We're going to do that on the random statement. And then we need to specify the variance covariance matrix in R. And that's the variance covariance matrix for epsilon. We're going to do that on the repeated statement. So when you run proc mixed, these are the three statements we're going to be focusing on: the model statement, the random statement, and the repeated statement. And again, if you're also not that familiar with the SAS programming language, each statement in SAS programming ends with a semicolon. So we'll start with a keyword. Each statement will have some required arguments or specifications, and then each statement also has some options that you can specify. Okay. I'm going to throw some more kind of notation at you here, but this is kind of another thing really to take away from this talk. We're going to mention how to pick a covariance structure. So you have some longitudinal data, you've collected some data over time, and if you're a subject matter expert, right, you probably know how you think that data should behave over time. So I mentioned I've got my Apple Watch and I've got my sleep data over time. I generally get about 7 hours of sleep every night. I mean, one of you may sleep a bit more, maybe you get 8 hours on average, maybe you get 6, something like that. But I don't really have that much variability over time in my sleep. So I'd kind of expect my sleep values to be pretty correlated, right? Maybe for some of you, your sleep is more sporadic, so your correlation wouldn't be as high, something like that. But most of us have, maybe sleep isn't a great example. Let's say you collected somebody's blood pressure, their systolic blood pressure, something like that. As a clinician, you kind of have an idea about that, how that should behave over time. So that informs really what you think about your outcome. Your outcome is in Y. So that's our actual outcome, like blood pressure or hours of sleep or something like that. But what I said is I told you that you had to specify the variance covariance matrix for two statistical quantities, gamma and epsilon, right? Now, most of us would look at this and say, well, I don't really know what gamma means. I don't really know what epsilon means. So how can I pick a covariance structure for these two quantities? Like, I don't really know, right? But what we do know is we may know some information about the variance covariance matrix of Y, which is our data. So here's how we get the variance covariance matrix of Y, of our data. And then this is where you can add your subject matter knowledge, right? Okay, so gamma, the random effects, they have covariance matrix G. Epsilon, the residual error, has covariance matrix R. We want to put these together to come up with the quantity for the variance covariance matrix of our data, of Y. And we're going to call its variance covariance matrix V. And again, this is notation in the SAS documentation. So here's a big formula for you. And this is going to inform how you actually fit your model for longitudinal data. So V, I said, is the variance covariance matrix of your data. So that's, if we're talking about blood pressure and I'm a clinician, that's where I would think about, what do I think the variability of blood pressure is at each time point? What do I think the correlation between blood pressure measured at different time points? What do I think that should be? All right, that's going to be reflected in V. And here's how we compute V. First, we take G, which is the variance covariance matrix of any random effects, and we multiply it on both sides by the design matrix Z. And this is a matrix transpose. And then we add to it the variance covariance matrix of epsilon. Okay, so you'll notice both covariance matrices from gamma and epsilon come in to the calculation of the variance covariance matrix of your data, but they come in differently. The residual error covariance matrix comes in additively. The variance covariance matrix of random effects, first we have to multiply it by its design matrix. All right. So that's just something to kind of keep in mind. Both gamma and epsilon, let's go back. Both gamma and epsilon have covariance matrices that are ultimately going to inform the variance covariance matrix of our data, which is why. All right. A little bit more notation here. We want to talk about how we're going to estimate the parameters in this model. let me once again go back to the statement of the model. So let's pick out all the things that we need to estimate in this mixed model. We need to come up with estimates for beta. This is really, in most cases, this is the reason that you've run your study. So for example, if I'm running a clinical trial and one of my predictors is treatment group. So I've assigned people to one of 3 treatments, and I want to test, is the mean blood pressure different for any pair of those treatments, right? That type of hypothesis is assessed by looking at differences in beta, in our fixed effects. So we need to estimate the betas. Then, and that's, in most cases, that's going to be where all your primary hypotheses live. But in order to get estimates for beta, we're also going to need estimates for all the parameters involved for the variance covariance matrices of gamma and epsilon. So we need to estimate the betas, we need to estimate all the elements of G, and then we need to estimate all the elements of R. So let's talk about how we're going to estimate beta B, my Greek. Anyway, let's talk about how we're going to estimate the elements of beta. So if you've had your first regression course, you may remember that when you have fully independent data, we use what's called least squares estimation in order to come up with this estimate of beta. So that's ordinary least squares, or OLS. Now, what we need to do is ordinary least squares estimation is not going to work in this case, because ordinary least squares is appropriate only when you have fully independent data. So what we're going to do is we're going to estimate the elements of beta using an extension of ordinary least squares, and that's called generalized least squares. And you don't need to obsess too much about this formula, except to notice that you'll see that this formula for beta, it's a function of 3 things. It's a function of X. This is your design matrix for your fixed effects. That's where all your data for the predictors comes in. So it's a function of X, it's a function of Y, which is the data for your outcome. And then it's a function of V hat, which is an estimate of your variance covariance matrix. All right, and then let's look at this estimate of V hat. So remember, V is the variance covariance matrix of your data. In order to come up with an estimate of V, so that's V hat, we then need estimates for both G and R. So that's G hat and R hat. So a key takeaway here is that in order to get estimates for your fixed effects in beta, and that's generally what you care about, like you want to do a hypothesis test relating your outcome to predictors. In order to get estimates for those fixed effects, you're going to need to first get estimates of your variance components. And that's not true when you have fully independent data. So let's introduce how we're going to come up with those estimates. And we're going to use what's called restricted maximum likelihood estimation. Let's talk about what we mean by that. What we're looking at in this picture is what's called the log likelihood of your data. And the likelihood is just the probability density function for your data. So if we're assuming our data are normally distributed, this is the normal distribution, something like that. And what we do is we express the likelihood, so this could be the normal likelihood, we express this as a function of the variance covariance parameters we want to estimate. And so in this case, let's assume we just have 2. We have 2 variances we want to estimate, sigma squared 1 and sigma squared 2. So we express our likelihood function as a function of those 2 parameters. And then what maximum likelihood estimation is going to do is it's going to find the solution for those 2 parameters that forms a maxima of the likelihood surface. Okay, so that's kind of right here. I think of it as finding a mountain, finding the tallest mountain in a mountain range. That's what I like to think of this as. So that's maximum likelihood estimation. Now I'm going to talk about some choices for covariance matrices, and we're going to need to talk about choices for R which was the variance covariance matrix of epsilon, your residual error. And we also will talk about a choice for G, which is the subject-specific random effects. So first, let's talk about R. And I'm gonna, pardon my continual scroll back to this slide, but so here's R. It's the variance covariance matrix of epsilon. Now the size of epsilon is the same as the size of Y, okay? So if a subject has, say, 10 time points in Y, they're going to have 10 rows in the variance covariance matrix of epsilon. Now that's not true for gamma, by the way. The dimensions of gamma are the number of random effects. Z has the same number of rows as Y, but gamma, if you have 2 random effects, for example, gamma would have 2 columns, things like that. But the dimension, the total number of rows in epsilon, is the same as the number of rows in Y. And so what we're doing when we're choosing a covariance matrix for R is we're directly trying to model the variance covariance matrix of Y. So kind of just keep that in your mind. And we're specifically going to talk about the case where there's no G. So in this case, we're going to talk about what's called a population average model, where we have no subject-specific random effects, and we're modeling all the correlation in Y through R. All right, so just kind of hold on to that idea. It's a model that just has an R matrix. So before we get to some possible choices, let's talk a little bit about why. Why do we care to spend some time to select an appropriate covariance structure? Because as I mentioned, this is one of those things that if you're a subject matter expert, a clinician, something like that, this is one of those things that you probably don't have great intuition about. Like how do I know what covariance structure to choose? Can the software just suggest some and then I could pick one? I mean, wouldn't that be nicer? And we're going to show you some different choices, but let's talk about why we actually care to spend some time picking a correct covariance structure. So if you choose a structure that is too simple, which is to say that if you underestimate the variability in your data, if you treat your data like it's independent when it's actually not independent, so you're treating it as independent, but it's actually correlated. So if you choose a structure that's too simple, then you risk increasing what's called your type 1 error rate. So a type 1 error occurs when you find a significant relationship that isn't actually truly present in your data. So you collect your data, you run your study, you run the analysis, and you find out, yay, there's a significant relationship between my outcome and my predictor. But we're making probabilistic assumptions when we find that relationship, right? And you can commit errors. Like you can find a relationship that actually doesn't exist in nature, in the population. And that's called a type 1 error. So you're finding relationships that don't actually exist. And in a clinical trial, for example, that you might find, for example, that drug A works better than drug B. But if that's actually an error, if that's spurious, then you would treat patients based on that evidence. But it turns out that in nature, drug A doesn't actually work better than drug B. So we don't want to commit type 1 errors. We don't want to inflate our type 1 error rate. So that's the first reason. If our covariance structure is too simple, if we assume too much independence and not enough correlation, we'll find too many significant effects. But then maybe we are really concerned, and so we're thinking, okay, I'm going to just use the most complex covariance structure I can find because I want to make sure that I model the correlation in my data, right? So if you choose a structure that's too complex, then you sacrifice statistical power and efficiency. And so what that means is you fail to find a true significant effect. So an example here would be maybe you have drug A and drug B treatments for some disease, and let's say it actually is true scientifically that drug A works better than drug B. but you collected your data, you fit your model, and you picked too complex of a covariance structure. And so in that case, you might fail to find that drug A actually is better than drug B. So you fail to find a true effect. And so then doctors wouldn't know to prescribe drug A versus drug B. So the goal here is we want to find a covariance structure that is neither too simple or too complex. And that sounds like a tall task because, again, these are statistical concepts and maybe we don't really know. But there are ways that we can assess this. So I'm going to go through some choices for covariance structures, common choices. SAS software has a much larger number of choices, but I'm going to show you some of the ones that make the most sense for longitudinal data. Now let's start with the default. I'm showing you this because this is the default in the software, but it's generally not going to be an appropriate choice for longitudinal data. The default is a covariance structure we talked about already, and that's fully independent data. This is the default on both the random and the repeated statements, which are the statements in SAS software that you use to model covariance structures. All right, so I'm pointing this out just to say that even if you don't explicitly choose a covariance structure in your software, you're still choosing one. You're choosing the default, and that's fully independent data. Let's look at the next simplest. So let me orient you to this kind of grid that's shown on the screen. So what we're looking at here is we're looking at the variance covariance matrix for a subject that has 4 time points. So time points are in columns, and then time points are in rows. And what we're looking at here is actually a correlation matrix, not a variance covariance matrix. So the diagonals here, this is the correlation of an observation with itself. So those will always be 1. And then the off-diagonal entries, these are going to be the correlation between time points within the same subject. So this box here, this is the correlation between time points 1 and 2 for this subject. Compound symmetry is the simplest covariance structure that you can fit that actually does incorporate some correlation in the data. And what we're doing here is we're simply assuming an equal correlation between all pairs of time points. So time points 1 and 2, time points 1 and 3, time points 1 and 4, they all have the same correlation row. Okay. Now you might think, well, maybe that's okay. I don't know. But this generally is a bad choice for longitudinal data because for longitudinal data, time points that are closer together tend to be more correlated than time points that are further apart, right? So in longitudinal data, we generally want to allow, for example, this correlation between time points 1 and 4. We'd like to allow for that to be smaller than this correlation between time points 1 and 2. So assuming an equal correlation between all pairs of time points, no matter how far apart they are, that's generally a poor assumption for longitudinal data. However, this covariance matrix, it does make sense for non-longitudinal data. So clustered data, which I talked about at the beginning. If you had students within a school and you thought students were correlated because of the abilities of the teacher or something like that, there's no natural ordering to students, right? And so an equal correlation matrix would make sense here. I'll also add that in this series, I'm also going to be giving one on multi-level models. And in multi-level models, this is what we're going to be using entirely, this kind of covariance structure. So there definitely are applications for this, just not longitudinal data. So compound symmetry, not a good choice. I'll make one other comment here, though. We only have an hour and a half together today, so the following point's not going to be nearly as obvious to you, but we mentioned that we have to estimate the variance covariance parameters. And in a mixed model, in longitudinal data model, we're going to have to use some sort of iterative method to come up with estimates of variance covariance parameters. Sometimes that iterative method does not converge, which means you don't get estimates of your variance covariance parameters. If you don't get estimates of variance covariance parameters, you don't get estimates of your fixed effects, you cannot assess any of the hypotheses in your data. So sometimes people will use compound symmetry just because this variance covariance matrix is pretty much guaranteed to converge. You're guaranteed to get estimates of the correlations. This type of covariance matrix generally leads to an algebraically solvable solution for the correlation. So people will use this because it will get them an answer, but that doesn't mean the answer is right. Like you are probably underestimating the true variance and correlation in your data if you use compound symmetry, even if it's the one that does give you converged variance covariance parameter estimates. All right. So many of you may be thinking, well, can I just be as flexible as possible? If I don't really know what variance covariance parameters to estimate or what type of matrix to use, can I just estimate a different parameter for every time point for every pair of time points? And so that's what we're looking at here. So once again, we have a person with 4 time points. We're looking at their variance covariance matrix here. The previous slide was a correlation matrix. This is a variance covariance matrix. So the diagonals, these are variances of their time points. And you might notice, due to the subscript 1, 2, 3, 4, we're estimating a different variance on each time point. So that's good. In general, it's nice to allow the variability of your data to change over time. That's particularly true in clinical trials. If you start with untreated patients that have some disease, and then you give them a treatment that works, the correlation at the start of the study will be pretty high. I'm sorry, the variability at the start of the study will be pretty high. But if your treatment works, you're going to be increasing or decreasing their outcome. So at the end of the study, their variability might actually be pretty low. So we have different variances for each time point. And then each of these off-diagonal entries, these are different covariances for each pair of time points. Right? This is called an unstructured covariance matrix. And you might think, well, this sounds great. Why don't I just use this? If I have a lot of data, I can estimate all these parameters. Well, there's a couple of drawbacks to this covariance matrix. The first one is the number of parameters that are estimated. So if you have t time points, you have to estimate t times t plus 1 over 2 parameters. So here, I've got 4 time points. That's 4 times 5, which is 20, divided by 2, which is 10. So I have to estimate 10 parameters here. That's not a big deal if I have 200 subjects, but if I have 20 subjects, estimating 2 time points is probably a bad idea. I'm sorry, estimating 20 parameters is probably a bad idea. This unstructured covariance also requires that you have the same time points on every subject. Let's say a little bit about that. So some of you may have data sets that are truly observational data. So you have repeated measures over time, but basically you get data on the person whenever they're available, right? And so in that case, you don't have the same time point on every subject. So maybe on subject 1, you've got 6 months, 9 months, 13 months. On subject 2, you have 2 months, 8 months, 10 months, something like that. So observational data, you tend not to have the same time points for every subject. But many of you also may be working on experimental studies, so clinical trials, where you, the researcher, design the time points. And in this case, you probably do have the same time points on every subject. So for example, you'd have a baseline time points. Maybe the patients come in weekly for the first few weeks, then they come in monthly, and then maybe you have a visit at 1 year, a visit at 2 years, something like that, follow-up. This unstructured covariance matrix does require that you have the same time points on all subjects. They can be unequally spaced, but you do need to have the same time points. We have a couple of simpler versions. So these are simpler, they're much simpler than unstructured, but more complex than compound symmetry. This one's very popular. It's called first order autoregressive, or AR1. So here we're still estimating one correlation row, like we saw in compound symmetry, but then we raise it to a power based on the number of time points between. So time points that are 1 time point apart get a power of 1, time points that are 2 time points apart get a power of 2, etc. This is substantially simpler than an unstructured covariance matrix. So this is popular, but it does require equally spaced time points, and it requires the same time points on every subject. And the reason it requires equally spaced time points is just due to the way these exponents work. Now I want to talk about, this is a covariance structure that is going to work for you if you have time points that are different on every subject, and you also have unequally spaced time points. Right, so far we've had some conditions like unstructured requires the same time points on all subjects, and then autoregressive requires equally spaced and the same time points on all subjects. If your time points are different for every subject and they're unequally spaced, you can use what's called a spatial structure. And there are many different kinds of spatial structures. This is the simplest one that I'm showing you, and this is called spatial power. So you'll notice in spatial power, we estimate one correlation row. So these off-diagonal entries have row. But then the exponent here, the actual values of the exponent include the actual time values. So here, T1 and T2, these are the time points for the first and second, or these are the time values for the first and second time points. So if it was, say, month 1, month 2, those are the actual values that would go in for T1 and T2 here. So what's nice about the spatial structures is they are a function of the actual observed time points. So these are going to be usable for any type of time points that you observe. Okay, I think we're about to get into a software demo. And I want to talk about a data set that I'm going to use for this demonstration, and this is the CD4 cell count data set. So these data, let me talk about the application here. So the way the HIV virus works, and so the HIV virus is the virus that ultimately causes the disease AIDS, right? So the way the HIV virus works is that it attacks an immune system cell called the CD4 cell. And so as the AIDS disease progresses, CD4 cell counts go down. The data for this demonstration, they come from the AIDS cohort study, and this study includes 369 men that ultimately go on to develop the AIDS disease. Measurements are taken roughly twice yearly, and I think the time span for these data is about 8 to 9 years. I also want to point out that these data are fairly old. I think they're from the late 80s. So these days we have very effective treatments for AIDS, or at least we do in this country, maybe not worldwide, but we have very effective treatments for AIDS in this country. But these data were taken around the height of the AIDS epidemic, which was in the late 80s. So some of the variables we have here, our outcome is going to be the CD4 cell count. So that's a number, I think, between, say, 0 and I think maybe the highest is 3,000 to 4,000. A CD4 cell count around 1,200 is normal. Anything above 1,200 means that you're someone with a normally functioning immune system, but you're sick. So your body is producing immune system cells because you're sick. So something above roughly 1,200 is normal, but fighting an illness. And then something below 1,200 means your immune system is starting to decline. And I think the smallest CD4 cell counts in this data set are things like 10 or 20. So very, very small. And we have some different predictors we want to relate to CD4 cell counts. So we have time itself. We have age at entry into the study. That doesn't change over time. And then we have predictors such as packs of cigarettes smoked per day, illicit drug use, yes or no. This population, by the way, had high rates of illicit drug use, number of sexual partners, and also a depression score. And most of those predictors are allowed to change over time. A few features about these data is this is an observational study. Basically, data were collected when the man could come in for observation. So maybe 2 to 3 years elapsed between the first 2 visits, maybe a few months elapsed between visits 2 and 3, basically just whenever the person could come in. So the time points are different for the subjects. And then I also want to show you something on this picture. So what we're kind of looking at is some trajectories of CD4 cell counts over time. There is an event called seroconversion that happens, and that is when the HIV virus is detectable in the blood. And in this study, we have the actual dates. So we have the visit dates, and then we also have a date for seroconversion. I'm not entirely sure how they came up with that date of seroconversion, but time points in the study can be negative. So any time points before seroconversion have a negative time value, any time point after seroconversion has a positive time value. And you might imagine that time points that are negative, you're basically healthy, right? This is before seroconversion. You have a normally functioning immune system. So we'd expect kind of CD4 cell counts in the beginning to be very normal. And then we'd expect them kind of to decline in these later years, right? So that's kind of the setup here. And here are some objectives of this study. The first objective is to estimate the average time course of CD4 cell count depletion. So we just want to know how are CD4 cell counts changing over time when the AIDS disease is being developed, or when someone is developing the AIDS disease. Does it take a year before your immune system is really low? Does it take 2 years, 5 years, something like that? Then we want to estimate the time course for individual men. So it makes sense that we're all different. We have different genetics, different environmental exposure, things like that. So maybe for some men, their CD4 cell counts dropped really quickly. Maybe for other men, they did not drop quickly, very slowly. We want to characterize the degree of heterogeneity across the men. So we're talking about estimating the variability of trajectories over time. And then we want to identify factors that predict CD4 cell count changes. So for example, age is one of the predictors. You might expect that someone who's 21, probably their immune system will work better and longer than someone who is 71, something like that. All right. Let me go into the software and just show you an example about how to analyze these data. And I am going to be showing you syntax in SAS. If you're not super familiar with SAS software, that's fine. You can just kind of sit back and watch the output and try to understand how we pick out different pieces of the output. All right. I'm going to be giving you guys information, by the way, at the end on how you can access the software that I'm using. And for faculty or educators in the group, I'm also going to give you information about how you can get access to course notes that go through these demonstrations. So our goal here is that we want to fit a model to this AIDS data set. And I'm using a platform called SAS On Demand for Academics. This is what the SAS On Demand for Academics launch page looks like. You log in, there's a launch button. You can create an account with non-academic email addresses or an academic email address, whatever you like. So this is usable by non-academic learners as well. And we're using what's called the SAS Studio framework. And just to give you a brief introduction here, on the left side, this is where we access all of our files. This is a cloud file system. So you do need to upload your files, and you can do that using this upload button. So I don't have direct access to the files on my laptop, but I can upload anything from my laptop. And I can also download anything to my laptop. I just can't access those files directly. So over here, we're accessing various program files and data sets. And so what I'm going to do is I want to fit a model to these AIDS data. And let me open up the data set in a viewer just so you can see it. All right. So here's our AIDS data set. This is a pretty, this data set doesn't have a lot of variables in it. So here, for example, this is our time. You'll notice that time is a real number here. So we've subtracted some dates, but it doesn't have, your time does not have to be like this. It could just be months, month 1, month 2, something like that. We have our CD4 cell count. We have age. This is age at entry into the study. So even though age obviously does change over time, it does not in our data set. We have packs of cigarettes smoked. This can be anywhere from 0 to 4. We have illicit drug use, coded as 0 equals no, 1 equals yes. This is number of sexual partners. I do want to comment, by the way, that several of these variables have had a constant subtracted from their values to make the values more anonymous. So age here, for example, we're not looking at children. We've taken, for example, an age of 50 and subtracted off, subtracted a number from it. So maybe if you added 30 to all of these ages, you would get the real age, something like that. Number of sexual partners is the same way. It's not the case that everybody has 5 sexual partners. I suspect that 5 really corresponds to either 0 or 1. Like most people have 0 sexual partners or 1. So we've anonymized, that's hard to say. We've added or subtracted a constant to many of these variables just to make the data values more anonymous. We have depression score, and then here's a key thing. So let's just look at how this data set is structured. If you have not ever fit a model to longitudinal data, we need to pay attention to how the data set's structured. So you'll notice here these first 3 observations, they're for subject 10002. The next several observations are for subject 10005, right? So we have a different number of observations for each subject. Then we have the next set from this person, 10029, right? Okay. So let's go ahead and fit our model. Now I'm going to do something here. I'm going to scale CD4 cell counts, which is to say I'm just going to divide them by 100. And the reason that we do that is, as I mentioned earlier, ultimately we have to come up with estimates of the variance components, right? And we have to use an iterative process to do that, a mathematical optimization algorithm to do that. And as I mentioned, that algorithm can fail to converge. And so we want to do some things to our data to encourage it to converge. And one of the easiest things you can do is try to scale your data. We're just going to scale our outcome, but you can scale your predictors as well. So CD4 cell counts, they do need to be positive, right? And in the real data, they're anywhere from 0 to, I want to say 3 to 4,000. So we're just going to divide them by 100. That makes all of our outcome values smaller and therefore makes the variances smaller. So I'm just scaling. And now I'm going to fit 2 calls to the mixed procedure in SAS. And so let's look at what we're changing in the mixed procedure. So the first statement is the mixed statement that calls the mixed procedure, and then we also specify the data set. In this case, it's the AIDS data set. On this model statement, this is where we need to tell SAS all the predictors in the model. Now I'm going to give you some, at the end, I'm going to point you to a slide where you can get some full-length course notes if you're an educator. And in that course, we actually do a bunch of exploratory data analyses before we fit this model. And in particular, we do some investigation to try to understand which predictors to put in here. So you wouldn't just start from this point. You do some exploratory analysis to understand your data first. But here, let's assume that I've done that. I've looked at my data already. And here's the model that I want to predict. So on my model statement, my outcome is going to be a variable, the scaled CD4 cell count. And then for the predictors, I have main effects for time, age, cigarette smoking, illicit drug use, number of sexual partners, and depression score. And then I've also included interactions between each of these and first order time. And in our exploratory data analysis, we also found that the relationship between CD4 cell counts and time can be described well with a cubic polynomial. So I'm also adding quadratic and cubic terms. All right. Now on my repeated statement, this is where I need to tell SAS that I have longitudinal data, that I want to choose a covariance structure to use to model the correlation or covariance structure between these data. I'm going to fit two models here, and I'm going to choose two different covariance structures. So this first one, type equals CS, this corresponds to compound symmetry. This one, type equals SP POW, this corresponds to that spatial power structure I talked about before. Spatial power is going to incorporate the actual time points, whereas compound symmetry will assume the same correlation between all pairs of time points. So it's very restrictive. Pardon me. So I want to fit these two models just to show you that you get different fits based on the covariance structure that you specify. I've also included some different options here to display the covariance structure for different subjects. So let me run these. So in SAS, you just hit the running man to run the code. I'll make this a bit bigger. I'm going to go down to the second piece of output, which is the piece of output corresponding to the model where we fit spatial power. And then I'll return to this output for compound symmetry. So I'm going to scroll down. Here's where the output starts. Now, one thing you can do in SAS On Demand for academics is you can send this output to different kinds of outputs. So we can send it to an HTML file, a PDF, or a Word file. I'm going to put this into just its own HTML file. So that's going to get rid of some of this stuff at the top and just make it a little bit easier to see this. And that'll just view in my browser. That just gives us a little bit more room to work with. So I'll scroll down here. Now, as you fit a model in any kind of software, including SAS software, you want to look at all the tables at the top. Like any kind of software is going to give you just some basic information about your model, probably in the beginning of the output. And most of us want to skip over that because it doesn't tell us anything particularly interesting, but it's always good to check that output to make sure you fit your model correctly. So at the top of our output, we have model information, just tells us the data set, type of covariance structure. Here's an important table, dimensions. So it tells us how many covariance parameters we're estimating. It tells us the number of fixed effects. So in this case, that's 14. It's 14 because that's the number of main effects and interactions and polynomial terms that we're estimating. And the reason we have 3 covariance parameters here, by the way, is in spatial power, SAS is estimating a residual variance, then it's estimating another variance in order to estimate a correlation. And then one thing I did is, which is optional, is I added a third variance that allows you to parcel out what's called measurement error, and that's using this local option. So that's why we have 3 covariance parameters. It tells us we have 369 subjects, and we have at most 12 time points on a subject, and at minimum 1 time point on a subject. You'll notice there's a table for iteration history. This tells you that an iterative process is being used to estimate the variance covariance parameters. So these 3 parameters are being estimated through an iterative process. And here we get a note, it says convergence criteria met. So yay, we have converged to variance covariance parameters. Now here's a big matrix to look at. This is the variance covariance matrix of the outcome of CD4 cell counts. So this is V. This is the variance covariance matrix estimated for a specific subject. So you'll notice that in in spatial power, we're keeping the variability constant on the diagonal. We'll look at other covariance structures that allow that to change. But then you'll notice that the off-diagonal entries, which are covariances, they are declining. So time points 1 and 12, they're going to be several years apart if you look at their time values. And their covariance is much smaller than, for example, time points 1 and 2. We have a table of the actual covariance parameter estimates. I want to turn our attention to two tables at the end. So this first table, this is a table of fit statistics. And you can use these statistics to compare models. And we're going to use these statistics to compare this model to the model that we fit with compound symmetry. So as an investigator, you want to find the best covariance structure, right? And so you'll fit a model with covariance 1, you'll fit a model with covariance 2, and then you want some sort of statistic that you can use to tell you which one of these models fits better. Each of these information criteria, or IC, this is a function of the likelihood of your data. So it's a function of your actual data values. And the reason that I'm pointing that out is because it's a function of your actual data values, the actual number here is meaningless. Like the fact that it's 11,735 instead of 9,735, that's dependent on your data. So the actual number itself is not interpretable. But what we can do is we can compare this number across models, and whichever model has the lower number is the better fitting model. And so here, when we fit spatial power, our AIC is 11,735. Let's go to this number in the compound symmetry. In compound symmetry, it's 11,850. So 11,735 is lower than 11,850. So this is telling us that our model with spatial power does fit better than with compound symmetry. And just a little more comments about this statistic, it's penalizing you for the number of covariance parameters. So the more covariance parameters you estimate, the bigger the penalty, but you may also be better estimating the likelihood, right? So smaller is better for these statistics. And in our case, you can use this statistic to show that spatial power is much better fitting than compound symmetry. Now this table at the end, this is ultimately what most of you would care about, right? You have collected data, you have scientific hypotheses that you want to test, and you want to ultimately come up with a hypothesis test to test each of those hypotheses. In this table, this provides a significance test relating each of these predictors to our outcome. On the right, we have a p-value for each one of those tests. So our test statistic is in this column. It's a t-test. We have degrees of freedom for our test statistic in this column, and then a p-value on the right. Now, you'll notice we have several interactions with time. We have several non-significant terms like time by drug, for example, very high p-value, time by depression, high p-value. So you wouldn't stop here. You would start to remove non-significant predictors here. So you wouldn't stop and interpret this model. But I will also comment here that we have so many predictors that involve time that it's actually hard to interpret these parameters, even if you remove some of the terms, right? So another, we're not gonna show you a graph in this session today, but ultimately, how you might want to interpret data from a longitudinal model is to create a graph. So instead of trying to interpret these parameter estimates, many of which involve time, you would create a graph that shows the projected trajectory of CD4 cell counts over time for different levels of these predictors. So for example, if you wanted to talk about how CD4 cell counts change over time for different values of age, you could create a graph of predicted CD4 cell counts over time for 4 different values of age. Okay. So that's some output that shows you how to interpret this mixed model for longitudinal data. And we're doing that using SAS Studio software. Now I want to show you another formulation of the mixed model, and this is important, and then we'll stop. And this is another type of formulation you guys will see a lot when your colleagues are modeling longitudinal data. So we just fit what's called a repeated only model. So this is a model where all the covariance structure is in R, okay? And therefore, the covariance matrix of Y, our outcome, is fully determined by R. So G, you might remember we saw this formula earlier. We just fit a model where G is 0. So this whole term goes away. And the variance covariance matrix of our outcome of our data is just equal to R. Now, this is a great type of model. This type of model is going to work really well if one of the specified covariance structures in SAS is what you want. This works really well when you have a smaller number of time points as well. But sometimes you might have a lot of time points for a subject. You might also actually care to estimate subject-specific trajectories over time. You might also have a covariance structure that isn't well modeled by the choices in SAS software. So for example, generally, it's the case that if time points are further apart in time, their correlation or covariance goes down, right? So the further apart they are, the covariance should go down monotonically. But maybe that's not true for your data. Maybe the covariance needs to go up, needs to go down and then up or something like that. And that's not a type of covariance structure that's going to be well fit using an option on the repeated statement. So in this case, you could fit what's called a random coefficient model. And this is where we're actually going to fit a subject-specific trajectory. So a trajectory for every subject. These are really great when you have a lot of time points. And intuitively, that makes sense, right? If I'm going to estimate a trajectory for a subject, I need more data for that subject. So if I've got 12 time points, I'm going to better be able to estimate a trajectory for the subject than if I have 2 time points, right? What we're going to do in a random coefficients model is now we need to estimate G, that variance covariance matrix G. And let's look at a picture here. So this black line, this is kind of what we estimated in the last demonstration. This is what's called a population average model. But with a subject-specific model, a random coefficients model, you can now allow subjects to have these dashed lines. So they're going to get their own trajectory. And here's how we'll parameterize it. We're still going to fit population average predictors. So let's say you have some predictor X, just one predictor X. You'll estimate a population intercept and a population slope. These parameters for beta are estimated over all the subjects, okay? But then in a random coefficients model, we're also going to estimate a random intercept that gets tacked on to beta 0 and a random subject-specific slope that gets tacked on to beta 1. So we'll also estimate A sub I star and B sub I star. And those are random deviations from the population intercept and slope. Now we're going to need to pick a covariance structure for G. Now here's another important takeaway. When you're fitting a covariance structure for G, the elements of G are random effects. They're not time points. So when we were talking about R, and we're talking about spatial power unstructured, we're actually modeling the variances and covariances of time points. But we're not doing that here. We're modeling the variances and covariances of random effects. So like of an intercept and a slope. So my subject might have 12 time points, but if they have 2 random effects, G is 2 by 2 for them. R will be 12 by 12 for them, and Y will have 12 rows for them. But G is 2 by 2. So there's only one choice, actually. So we like simplicity, right? There's only one choice for the G matrix in terms of the variance covariance matrix, and that is unstructured. So we want to allow all the random effects to get their own variance, and then we want all pairs of random effects to get their own covariance. So if you're using the random statement, the only covariance structure you should specify is unstructured. So that's nice. Let me see how we're doing on time here. I've got about 15 minutes. So let's go to the software. And let me find just in my notes here which program I'm going to bring up. Sorry about the pause. Let's see. So I'm going to go into my files, and this is program 7. So I don't want to obsess too much about the syntax here, but I want to show you what has changed. So we want to fit this random coefficients model that allows for subject-specific trajectories. Let's remind ourselves what we just fit. So before we use the repeated statement, that fit a covariance structure for the residual error in R. Now you'll notice we're going to fit a similar type of syntax, but now we're going to use the random statement in SAS. So this is going to model random effects. We need to choose some random effects. Now the goal when you're choosing random effects is you don't want to have a random effect for every fixed effect. So I wouldn't want to simply just copy all this business and put it on here, okay? You want to choose a parsimonious set of random effects, and you want to choose the ones that you think will be related to the covariance structure. Because every random effect that you include increases the size of the G matrix. And remember, it's an unstructured matrix, so we'll have to estimate a lot of parameters if we have a lot of random effects. So here, I'm fitting 4 random effects, a random intercept, and then a random effect for each of the time parameters. I'm using unstructured covariance, and then I'm printing some of the matrices. So I'll go ahead and run this. And the output is going to look very similar. Like we have changed the covariance structure, but the actual output that we get contains mostly the same display boxes. So I'll scroll down. Notice we now have 11 covariance parameters. I think the model that we fit before had 3, so we are estimating more. Our iteration history, we did converge. And here's our G matrix. So the elements of G are random effects. And this matrix describes the variances of those random effects and also their covariances. But then we can also print the actual variance covariance matrix for the data for the subject. So this is the same subject we looked at in the previous demo. And let me put this in a web page as well, just to make it a little easier to see. So here's the variance covariance matrix of the outcome when we have this subject-specific model. And you'll notice that in this one, the diagonal entries change, right? So when we specified spatial power, we actually restricted the variance of the outcome to be the same over all time points, which is, considering we have a disease process that is happening, the variability of CD4 cell counts we expect to really decline over time because people are all getting sicker. Whereas at the beginning of the study, they are healthy and will have much bigger variance. So this model might fit better because we're allowing the variance to be different at different time points. You can also export, or I should say just print estimates of all the random effects as well. And here's our table of variance covariance matrix parameters here. So these are the parameters of the G matrix. Now I've gone through this very, very quickly. And this is kind of an introductory talk on some of the concepts of longitudinal data analysis and the 2 types of models that you might want to use. The repeated only model, which models only the residual variance, and then this subject-specific random effects model. So those are 2 types of models. As I mentioned earlier, you can also apply these types of concepts to non-normal data as well. So maybe your outcome is binary, yes or no, or maybe it's an ordered category. You can fit those types of models as well. To conclude, I wanted to show you a few resources for future learning. So the software that I demoed today is called SAS On Demand for Academics. This is free SAS software. It's available for educator, students, and independent learners. It runs what's called our SAS 9.4 software. I showed you the programming interface. There's also what are called SAS Studio tasks. These are point and click tasks that will allow you to generate SAS code through some clicks if you're not familiar with the SAS programming language. As we saw, this runs in the cloud. There's no installation on your computer. It's going to look the same regardless of operating system. Internet access is going to be required since this is cloud software. And you can register for SAS On Demand for Academics at sas.com/on-demand. And just a few more comments. This is full SAS software. It's not a limited educational version. So it's got all of our SAS statistics procedures, our base SAS language, which is the programming language for data management, data creation, data checking, reporting, all kinds of things. We have our matrix language, operations research, quality improvement, and also our time series procedures as well. So this is a full version, not a limited educational version. Lori's put into the chat, this is a quick tutorial about SAS On Demand for Academics from our trainer, Dominique. So this is almost 10 minutes long, 9 minutes long. So a little introduction to the interface and how to get on to SAS On Demand for Academics. I wanted to mention to educators that are on the call, every summer we like to have a conference in the summer where we invite educators to our campus in Cary, North Carolina. And you can meet with us, and we have a bunch of different programming, and you get to eat in our nice cafes, and people just like to visit the SAS campus. The last time that we did this was in 2019, before the pandemic. So we're excited that we're able to do this again for the first time. And we're having our first conference for educators this July 18th and 19th. And Lori put into the chat the link to register for this. So this is at our world headquarters in Cary, North Carolina, but it's otherwise a free conference if you'd like to attend. For those of you that are students, we do have internships at SAS. We have over 200 interns every summer. And I wanted to put this slide up here because the hiring process for our internships starts really early. So if you want to be an intern for next summer, you would apply this September. Then there are interviews starting in October, and then your internship would start in May. So the actual application process starts in the fall. And Lori put into the chat a webpage that gives you some more information about our internships. The internships conclude in a poster presentation by all the interns. I've always been very impressed by the work that our interns do, and they are paid internships as well. We have two portals that provide a variety of learning resources for you. All of these resources are for free. The first one is SAS Skill Builder for students. The biggest attraction in SAS Skill Builder is you get access to over 20 free e-learning courses about SAS programming, statistics, things like that. You can register at sas.com/skillbuilder. Here's just a picture of the launch page for SAS Skill Builder. You'll click on this Start Learning button, and this will take you to a list of e-learning modules. They're organized in kind of these 5 different groups, but each one of these groups, together, these groups give you access to over 20 free e-learning courses. And there are a variety in the statistical analysis section. In particular, we have a great Statistics 1 e-learning. Each of these e-learnings is also organized into a certification pathway if you're interested in doing that. And so these are certification exams where you take a test, and that allows you to demonstrate to employers that you have a certain level of SAS skill. For educators, we have the SAS Educator Portal. The best thing about the Educator Portal is that we give you access, free access to over 100 teaching kits, including a teaching kit for the slides that I have discussed today on longitudinal data analysis. You can use these teaching kits to provide slides that you teach directly from. You can distribute the slides to your students. You can also use them for your own professional development or to give you ideas about your curriculum. They include the slides, the course notes, the data sets, and the programs. We also have a variety of classroom activities that you can find in the educator portal. You can access the educator portal at sas.com/teach. And here's the homepage for the educator portal. The teaching kits are available from the Browse Instructional Resources area. And I wanted to point out, and the educator portal is only for educators, it's not for students, but I did want to point out that full course notes, including the slides that I discussed today, are available through the SAS Educator portal. These are course notes for a 3-day-long longitudinal data analysis course, where we go through an exploratory data analysis for longitudinal data. Then we show you how to fit a variety of models to your longitudinal data. And you can access this course through the educator portal. I've got 5 minutes left. I'm happy to take any questions. If, as you think about this seminar in the future, if you have any questions, I've also listed our email addresses here. Mine is jacqueline.johnson@sas.com, and you can also email Lori at lori.downen@sas.com. Any questions? And you can access the Skill Builder portal for students. Faculty can access that as well. I recommend that that faculty do register for SAS Skill Builder, because then they can see what their students see. Well, I'm going to stick around for any questions, but if you don't have any questions, please feel free to log off. It's been my pleasure to be here with you today, and I hope you have a great rest of your Thursday. Thank you.
Thank you so much, Jacqueline. It was wonderful. Thank you. Thank you.
Sure.